In this video for Computer Science AS Level 9618, we're going to be taking a look at bitwise manipulation, specifically binary shifts and manipulating bits. Let's go ahead, let's take a look at the learning targets. They want us to be able to show an understanding of and be able to perform binary shifts. We'll be doing that today, and those shifts include logical, arithmetic, cyclic, left and right shifts, and to show an understanding of how bit manipulation can be used to monitor or control a device. We're going to be carrying out some bit manipulation operations. We're also going to be testing and setting bits using bit masking. So what are shifts? Well, it involves moving bits that are stored in a register either to the left or right within the register itself. Now, bits within the register are used for different purposes, and we'll be taking a look at that later today. Now, there are different types of shifts you need to be familiar with. One is a logical shift, an arithmetic shift, a cyclic shift, left shifts, which are used for multiplying, right shifts, which are used for dividing. So let's go ahead and dive into these logical shifts. Now, bits shifted out of the register are going to be replaced with zeros, which means when we have open spots, we're going to fill them with zeros. So imagine we have the following binary number. We have 1010 and then 1111. We want to shift left logically 3 places. That would remove the first 3 bits, changing it to 0, 1, 1, 1, 1, and then 0, 0, 0. Well, what happened to the first 3 bits, the 1, 0, 1? We're getting rid of them because we are shifting the binary number to the left in this example. Because we're shifting it to the left, we have no room for the 1, 0, 1, so it literally just disappears. Now, there's no math being performed on this one. We are not shifting to the left because we are multiplying. It's asking us to shift logically. Now, this does affect the value in the accumulator, and we'll look at some practice problems today to make that clear. So let's imagine we have a binary number 0110 1100. Now, because this is a logical shift, we're not performing math. So let's shift this 1 place to the left. So here's my binary number. Here's my new number. Well, how did I get this number? Well, I shifted every bit 1 place to the left. This one shifted 1 place to the left. This second one shifted 1 place to the left. This 0, 1 place to the left. And every bit shifted 1 place to the left. What about this 0? The 0's out of there because we have no room for it. We shifted everything over and it got pushed right off the ledge. Where did this 0, where did this one come from? Well, it's an open bit, and all open bits at the end of shifts are replaced with zeros. So now let's shift it 2 places to the left. We have that same binary number. This time, if we shift it 2 places to the left, I'm going to take this 1 right here and I'm going to shift it over. What happens to this 0 and 1? We ain't got room for it. So everything shifts over 2 places to the left. Now, I am left open with 2 open places. Where did those zeros come from? We've replaced the open bits with zeros. So let's take a look at this logic shift practice problem. A general purpose register is the accumulator. The accumulator in this system contains 6 bits. Inside the register is currently the value of 12. A logical shift is performed that shifts bits in the register 2 places to the left. Show the new binary value after the shift. So here is the binary value of 12. I simply work it out. And there's my binary value of 12. So I show Cambridge or my professor if I'm at a university that I know how to take a denary number and transform it into a binary number. Now, they want us to shift 2 places to the left. Now, when you're shifting to the left, you want to start from the right-hand side. That way everything lines up. If you start from the left, you could easily make a mistake. Starting from the right is easier. So I'm going to take that 0. I'm going to shift it 2 places to the left. I shifted it 1, 2 places. I'm going to take this 0 and I'm going to shift it 2 places to the left as well. I'm also going to take this 1. I'm going to shift it 2 places to the left. I'm going to take that final 1, shift it 2 places to the left. Now, what do I do with these zeros? There is no room for them. They've been pushed off the cliff. We have shifted to the left. We don't have room for them. They gotta go. So they literally just disappear. Now, what about these 2 open spots? What do we do with those open bit positions? We simply place them with zeros. The zeros here at the beginning do not shift over to here. It's just a coincidence that both of these are zeros and both of these are zeros. When you're doing a logical shift, everything that gets pushed off does not go anywhere, it just disappears, and then we replace the open position with zeros. So what is the denary value after the shift has been performed within the register? Well, this is going to be done in 2's complement. So we have 1, 2, 4, 8, 16, negative 32. Negative 32 plus 16 is negative 16 because it is in 2's complement. Let's take a look at another example. A general purpose register is the accumulator. The accumulator in the system contains 6 bits. Inside the register is currently the value of 17, so we've loaded that here, or I have loaded that into the binary representation. A logical shift is performed that shifts bits in the register 3 places to the right. Show the new binary value after the shift. So we're going to bring up our table, and all we're going to do is we're going to start from the left this time because we're shifting over to the right 3 places. So I'm going to take that 0, I'm going to shift it over 3 places to the right. I'm going to shift it 1, 2, 3. Then I'm going to take that 1, I'm going to shift it over 3 places, and then the 0, 3 places. I am now out of room. What happens to the 0, 0, and 1? It literally just disappears. What do I do with these remaining open bit positions? I fill them with zeros. And just like that, we have answered number 3, which brings us to number 4. What is the denary value after the shift has been performed within the register? 1, 2. That's it. 2. We're done. The new value is 2. It is that easy. If you're feeling overwhelmed, don't. The more time you spend with this, the easier it can get. And the most important thing you need to understand is that you can do this. So an arithmetic shift. Now the sign of the number stays. This means the binary number is in 2's complement. Now the arithmetic shifts are used for multiplying and dividing, not adding and subtracting. We did binary arithmetic earlier in the year, but now we're learning how to multiply and divide. If you're shifting to the left, you're multiplying. If you're shifting to the right, you're dividing. Now there is one small thing that you need to know. Well, I guess it's not really a small thing, it's a big thing. If you shift 1 place to the left, you're multiplying by 2. If you shift 1 place to the right, you're dividing by 2. That is because 2 to the power of 1 is 2. If you shift 2 places, you're multiplying or dividing by 4. That's because 2 to the power of 2 is 4. What about if we shift 3 places? What is 2 to the power of 3? That is 8. So if we shift 3 places, we are multiplying or dividing by 8. What about 4 places? Well, that would be 16. So that is what you need to know, because they may say, we want you to shift to the left. Well, are we multiplying or dividing? So let's take a look at an example with the number 48. Now in binary 2's complement, it's 1101, 0000. So a 1 at the beginning means we have a negative number. In this example, we are going to have the bits arithmetically shifted to the right 3 places. Now, to the right means what? Are we multiplying or are we dividing? We're dividing. Now, 3 shifts to the right means divide by what? Well, what is 2 to the power of 3? That is 8. Now, you may be saying, well, what does it matter if I can just shift anyway? Why do I need to know this? Well, that's going to be made abundantly clear in just a few minutes. So here's our binary number. Let's work it out. So once again, our binary number, we're dividing by 8, shifting to the right 3 places. Here's my binary number. And what we're going to do is we're going to bring in this table. If you'd like to pause here and give this a try, feel free to do so. All right, now for this one, the sign stays. So we have a 1 in the left-hand corner. That 1 goes in the first box, but we can't lose it though. It also goes in the second box. It also goes in the third box, and it also goes in the fourth box. Why? Because that sign has to stay. We don't drag the 1 all the way over here. I mean, I guess you could and then fill it in with 1s, but you need to understand that the sign stays. So until we get to where it is going, we are putting that sign in every box. Now, the second one, all we do, it's not a sign. We just shift it normally 3 places to the right. So there's our 1s. We shift it to the right 3 places. The 0, we're also going to shift to the right 3 places. The 1, we're also going to shift to the right The 0, we're also going to shift to the right. Now, what do I do with these 3 zeros on the end? Nothing. They disappear because we got no room for them. Now, we did negative 48 divided by 8, which is negative 6. Let's check our binary number, and let's make sure we got negative 6. So 1, 2, 4, 8, 16, 32, 64, negative 128. So I know I'm starting with negative 128. Negative 128 plus 64 is 64, negative 64. Negative 64 plus 32 is negative 32. Negative 32 plus 16 is negative 16. Negative 16 plus 8 is negative 8. Negative 8 plus 2 is negative 6. So if they're asking you to shift to the right, doing an arithmetic shift, you have the ability to check your answer. You know that negative 48 divided by 8 is negative 6. So you'll be able to check your answer to make sure that you're correct. All right, let's do this one. 6 bits are used, 16 divided by 4, and negative 24 divided by 8. If you'd like to pause the video and give this one a try, I strongly encourage you to do so. All right, so let's see what you came up with. So we are doing 16 divided by 4. Now, we have to ask ourselves, are we going to the left or are we going to the right? Because we're dividing, we're going to the right. We're dividing by 4. How many shifts to the right is that? Well, it can't be 1 because 2 to the power of 1 is 2. What about 2 shifts to the right? 2 to the power of 2 is 4. We have found out how many places we're shifting. Now, we have a positive number. This sign stays, which means the 0 goes here. It goes here, and it goes over here. So let's start working that one out here. So the 0, we're going to put it here. We're going to put it here, and because we shifted 2 places to the right, we're going to put it in its final place, and then we're going to keep that sign in the first 3 boxes. Then we bring this 1 over. I bring the 0 over, and I bring this final 0 over. What about the 2 zeros I have left? You know the drill by now. They simply disappear. What is 16 divided by 4? That is 4. When I look at my binary representation, I have 1, 2, and then I have a 1 in the 4 position, and 16 divided by 4 is 4. All right, let's take a look at another one. 6 bits are used, negative 24 divided by 8. So let's see what you came up with. Now we have a 1. This sign has to stay. We are dividing. Are we going to the right or to the left? We are heading over to the right. It does say a right shift practice problem, but how many places to the right are we going? Are we going 1 place? Well, 2 to the power of 1 would be 2. This is not a 2. This is an 8. What about 2 to the power of 2? Well, that's 4. This is an 8. What about 2 to the power of 3? That is 8, so we're simply shifting to the right 3 places, but don't forget, we got to keep this sign. So this 1 goes in the first box. It also goes in the second box. It goes into the third box. It also goes into the fourth box. We have taken this 1, we have shifted it over 1, 2, 3 places, and the boxes or bit positions preceding it, we have filled in with the same sign, which is a 1. I take this 0, I shift it over. I take this 1, I shift it over, and these zeros, you know the drill, they simply disappear. Now, what is negative 24 divided by 8? Well, that is going to be negative 3. So here I have 1, 2, 4, 8, 16, negative 32. When I have a 1 right next to it, I cut it in half. This is negative 16. I have a 1 right next to that, which means I cut it in half. That is negative 8. Negative 8 with the 1 right next to it means I cut it in half, negative 4. So I have negative 4 plus 1, which is negative 3. So I'm able to check my result and make sure that it is correct. So what about 7 bits? 32 divided by 8. Well, we're moving to the right 3 positions. I'm going to take that 0, and I'm simply going to shift it over. Then I'm going to move over this 1, and the 0, remember, I'm keeping the sign. I shifted over 1, 2, 3 places, and I'm keeping the sign in the preceding boxes. I keep shifting everything 3 places. I'm left over with 3 zeros. They simply disappear. And what is 32 divided by 8? That is 4. 1, 2, 4. I have a 1 in the 4 position, and I know my answer is correct. What about negative 42 divided by 2? One more time. We have this 1 here. We got to keep that sign. We're shifting to the right 1 place. So my 1's going to end up 1 place to the right, and every place before its final place is going to be holding that sign. So I bring my 1 here. I bring it over here, and then I simply keep shifting everything 1 space to the right. I just move that 0 over one spot to the right, the 1 one spot over, this final one spot over, that 0, it's gone. I don't have any room for it. What is negative 42 divided by 2? That is negative 21. And when I work this out, it comes out to negative 21. Now, left shift. Well, we want to perform the following calculations showing the correct shift of places on the bits. The first one is 16 times 2, then 19 times 4. If you'd like to give this a pause and try it out, feel free to do so. And we're back going over the answers. That could be a very short wait, depending on whether or not you pause the video. So 6 bits are used. We want to do 16 times 2. So what we're going to do is, because we're going to the left, we're going to start from the right. We're multiplying, so we're going to the left. And how many positions to the left are we going? 1. I simply move everything over. This 0, I shift over. This 0, I shift over to the left. And I just keep shifting each bit one place to the left, and I think we might have messed up. Did we mess up? No, we didn't. We get what's called an overflow. When I shift everything over, what happens is I wind up with this 1 in the negative position. I cannot represent positive 32 with 6 bits. The highest number I can represent is 31. So even when I have it worked out properly and I put in the 0, I'm going to get an overflow. I cannot represent 32 with 6 bits. Now, let's take 7 bits, one that can work, which is 19 times 2, which comes out to 38. Now, we're multiplying, which means we're going to swing over to the left, or shift to the left. How many spots are we going to shift? 2 to the power of 1 is 2. That tells me I'm going to shift to the left 1 bit, or 1 slot for each bit. So all I'm going to do is take my binary number, I'm going to shift it over 1 place to the left, and now I don't have any room for that 0. It disappears. What do I do with this leftover box? I put in a 0, and I'm looking for 38. 1, 2, 4. 4 plus 2 is 6. 8, 16, 32. What is 32 plus 6? Well, that is 38. So we know our answer is correct. You got to make sure you're looking at the amount of bits that are used and make sure you can represent the number that it should come out to. In the previous problem, we couldn't represent it, which is why we got what's called an overflow. Now let's talk about cyclic shifts. No bits are lost during the shift. When the bit is shifted out of the end, it shows up at the other end of the register. It literally cycles around. So imagine we have 1, 0, 1, 0, 1, 1, 1, 1. Now the reason I've put this in colors is so you can see where it goes. So if we're shifting 3 places to the left, we're shifting this 3 places to the left. Well, it swings back around. 1, 2, 3, ends up in the 3rd position. The 0, 1, swings back around, 2, 3. This one, we swing to, or shift to the left, 3, 1, 2, goes back around, 3, and then everything else shifts to the left, 3 as well. That is what a cyclic shift is. It just swings around to the other end. Now, bits are shifted to the left, giving direction for a logical shift. Bits can be shifted to the left, meaning multiply for an arithmetic shift. Bits can be shifted to the left, giving direction for a cyclic shift. So those are the various left shifts. Now, right shifts, they could be shifted to the right, giving a direction for a logical shift. They can be shifted to the right, meaning we are going to divide for an arithmetic shift. They can also shift to the right, giving a direction for a cyclic shift. So when you're looking at a left-right shift, you have to ask yourself, am I doing a logical shift? Am I doing an arithmetic shift? Or am I doing a cyclic shift? So how do we know to shift? How do we know what to do? Well, we can look at assembly language. So here it says bits in the accumulator are shifted logically in places to the left. Zeros are introduced on the right-hand end, which we saw earlier today. Now that we understand that, this makes a lot of sense. We know this stands for logical shift left. LSR, logical shift right. So we have the opcode, we have the operands for shifts, and you need to be familiar reading assembly language for logical shifts. They're always going to be done on the accumulator. There's not an exception to that. And you can always look in here. But now that we understand how logical shifts work and that we're going to replace the open bits with zeros, this makes a lot more sense. Now, let's talk about the last part, which is monitoring and control devices. So shifting bits doesn't help with monitoring and control devices whatsoever. It doesn't make it a monitor device, doesn't make it a control device. Now, what it does do, though, is that each bit could be used in a register as a flag. Now, here's an example. We have 8 bits where each individual bit shows whether data has been processed or not, or it controls a certain function. Now, we're going to look at an example here in just a bit. We are using the opcodes AND, XOR, and OR. These work exactly like the logic gates do, and when we combine them with the bit mask, we can change whatever bit we want. So AND is used to check if the bit has been set, OR is used to set the bit, XOR is used to clear a bit that has been set. What in the world does that mean? Well, let's take a look at some examples here. So let's take a look at controlling lights. So let's imagine we have a control room where all lights for the rooms of a museum are connected, as well as the doors. There are 3 rooms, and each room has an automatic gate that closes, blocking off the room. Now, this has been set up this way, so at night, they can switch all the lights off and bring the gates through bitwise manipulation. So bits 1 to 3 on the far right indicate if the lights are on or off. So bit 1, 2, and 3 are controlling the lights. Bits 4 to 6 are controlling if the gate is enabled or disabled. So here we can see in bit 6, this door is enabled, bit 5 and 6 are disabled, and that bit 1, 2, and 3, all the lights are on. What about bit 7 and 8? They're not used. And they will tell you on the exam what they're being used for. And they're not just going to leave it open. They'll simply put in not used. And we need to know what they're for. You have to know. You can't just look at a series of numbers and know what they're doing. They'll tell you what it's for. So according to this, which room have lights on and are open? Well, rooms 1, 2, and 3 have their lights on. What rooms are open? Bits 4 and 5. If I look at room 6 or bit 6, that lock is engaged. It's blocking off the room. So according to this, which room have lights on and are open? All I did was copy this over to the next slide because we're about to do some bitwise manipulation. Now, all 3 rooms have lights on indicated by the ones in the first 3 bits. Rooms 1 and 2 are open indicated by the 0 because it means the gate is not engaged. At night, they want to shut all the lights off regardless of whether they are on or not. Well, how can we control that? We control that with what is known as a bit mask. Now, a bit mask is a binary number we set to manipulate the bits, and we're going to be using AND, OR, or XOR. So I need to get these ones, I need to get them to 0. Now, we know we want all the gates engaged, shown with all ones, and all the lights shown off with zeros. Will the AND, OR, or XOR allow us to engage the gates? So we can do that first, and it's going to be OR. Will the AND, OR, or XOR allow us to turn off the lights? It's going to be AND. And you may be saying, how in the world did you get that? Well, we're going to go over how we got it right now. So here is what we have. This second one right here is our bit mask. So we're starting with the gates. All gates need to be engaged. So we need to set room 3, room 2, and room 1 to 1. We need to engage those gates. So this binary number is showing the current state. Here, using OR, this is our bit mask. If I set my bit mask to 1, 1, 1, 0, 0, 0, I run it through just like I would an OR gate. So the result comes out to 1 or 0. What is the result of 1 or 0? That is 1. What about 1 or 0? Again, that is 1. 1 or 0, that is 1. But I'm looking to close the gates or to bring up the gates. What is 0 or 1? It is 1. What is 0 or 1? That's 1. What about 1 or 1? That is 1. So what we did was we used the bit mask with the OR operand, and what that does is we are able to manipulate the bits to get them to do exactly what we want them to do, and we're able to shut all the gates. So push of a button, doesn't matter if they're open or closed, by using OR, we can get the bits to set exactly what we need them to set to. So now that the gates are engaged, we set them all to 1, we need to shut the lights off. So here's our current state. We have all the gates locked, the lights are on. So what I need to do is I need to use and what that will do is it will shut these off. Now I can have these as ones because I want to leave those gates engaged. I know they're engaged. I also want to set these to off. So the result, what is 1 and 0? Works just like an AND gate. It becomes 0. 1 and 0 is 0. 1 and 0 is 0. But what about when both of them are 1? They're 1. So now I have the gates engaged. They are up, they are locked, and the lights are off. We are ready to leave for the night. What about testing a sensor? Well, we got to do XOR. So 4 bits are used to show if a sensor's data has been processed or not. Now, once it has been processed, it needs to reset so the new data can be processed. In the following scenario, which bit has been processed? When we look at our data, we can see that bit 3 has been processed. And when we reset the bit showing the data has been processed, we need to make sure we affect that bit only. All bits should be in the reset position. So here's our current state. We know bit 3 has been processed. So the current state, we need a bit mask. So we're going to use XOR because what we want to do is manipulate this bit only. So I have to come up with a bit mask. I need to ask myself, how do I get all of these to 0 using XOR? Well, my bit mask would be right here, 0, because 0 XOR 0, 0 XOR 0, 1 XOR 1, and then 0 XOR 0. What's the result of these? 0 XOR 0 is 0. What about when I have 1 XOR 1? That comes out to 0 because it can be one or the other. It can't be both. And now all of them are in the reset position. So let's wrap up with assembly language. Now you can use assembly language to do this too. You can have LDD sensors, which you're going to load the sensors into the accumulator. You're going to use the AND binary mask with the binary number 1, 0, 0, which is going to select bit 3 only with AND. We're going to compare it, check bit 3 to see if it is set. Then we're going to use, after the compare, we're going to use that jump process. We're going to have JPN. If not equal, jump to a process routine. In other words, jump to a process routine if it's not set. Then we have LDD sensors. We're going to load sensors again to the accumulator. We're going to check and make sure they're all at 0. We're going to switch 3 back to 0 without affecting the other bits. And that is going to be it for this podcast. I hope you found this video helpful. If you did, make sure to give it a thumbs up and subscribe to help the channel grow. And we'll see you guys in the next video.